not spirits or echoes of memory, but something even more elusive and fundamental. These invisible presences lie hidden inside the atoms that compose your very being. Strangely enough, no one has ever seen them, touched them, or proven beyond doubt that they truly exist. Yet everything around you depends on them. They are called quarks. They exist deeper than protons and neutrons, beneath the very foundation of all matter that gives you mass and structure. If atoms are like the musical notes that compose reality, then quarks are the vibrations themselves, the invisible rhythm behind the song of existence. But to understand how we arrived at the idea of such ghostly particles, entities that might not even be particles in the traditional sense, we must first uncover an older illusion, the illusion of solidity. You seem solid, your hand, the floor, the walls, the objects you touch. But this solidity is a trick played by your senses, a beautiful deception necessary for survival. In truth, the material world is mostly empty. Atoms are not compact marbles, but vast regions of emptiness where probabilities dance. The tiny nucleus sits at the center, surrounded by a cloud not of matter, but of possibilities. Electrons don't orbit like planets around a sun. Instead, they blur in a haze of probability, existing everywhere and nowhere at once until observed. Even that nucleus, dense and heavy, hides another secret. It is not fundamental either. Inside protons and neutrons live smaller entities, stranger ones, quarks. A proton is made of 2 up quarks and 1 down quark. A neutron contains 2 down quarks and 1 up. They are bound together by the strongest known interaction, the strong nuclear force, held tight by particles called gluons, the messengers of that invisible bond. But if you try to pull one quark free, the force doesn't weaken, it strengthens. Tug hard enough and instead of separating them, you summon new quark-antiquark pairs from the vacuum itself. The universe refuses to let quarks exist alone. Every attempt to isolate one ends in failure. Nature seals the chamber shut. Yet the math never lies. We know quarks exist not because we've seen them directly, but because their influence is undeniable. Particle collisions behave exactly as they should if quarks are real. The trails of energy, the decay patterns, the way debris spreads from a high-speed collision, all align with quark-based predictions. But are they genuine physical objects, or just elegant placeholders for something deeper? At CERN's Large Hadron Collider, protons are accelerated to near-light speed and smashed together, recreating the universe's earliest moments. And in that chaos, we glimpse evidence of quarks, never directly, but in the echoes they leave behind. It's like watching ripples on water and deducing the shape of a stone that has already sunk out of sight. The deeper we look, the stranger it becomes. Quarks are not tiny spheres with surfaces or edges. They defy the very idea of physical shape. They are better described as excitations within invisible quantum fields, disturbances rather than things. What we call matter is not solid substance, but oscillation, vibration, a pattern of energy. You, me, everything around us, all are collections of standing waves pretending to be solid beings. Solidity itself is a mirage. Matter is probability, and what we call identity is a brief choreography of motion occurring near light speed. Quarks are the silent conductors of this performance, unseen yet orchestrating the illusion of permanence. You are made of ghosts, ghosts you can never touch, that you can never see, but without which nothing could exist. Strange, isn't it? In 1964, physicists faced a crisis. Laboratories around the world were discovering an overwhelming number of new subatomic particles, a zoo of bizarre entities. The once simple picture of the atom had collapsed into chaos. Protons, neutrons, electrons, mesons, baryons, kaons, pions, hundreds of short-lived particles appearing and vanishing in flashes. The tidy models of classical physics had disintegrated under the unpredictability of the quantum world. Then came Murray Gell-Mann, a theoretical physicist with an unmatched ability to find order in confusion. He proposed that these numerous particles were not truly fundamental, but composed of smaller building blocks, combinations of a limited set of constituents. He called them quarks. The name itself was unusual, borrowed not from Latin or Greek, but from James Joyce's experimental novel Finnegan's Wake, where the phrase 3 quarks for muster mark appears. Gell-Mann pronounced it to rhyme with fork, even though Joyce intended it to rhyme with lark. But in a universe where certainty was fading, a little contradiction felt fitting. At first, quarks existed only as mathematical inventions, elegant symbols that made the particle zoo finally make sense. In Gell-Mann's framework, protons and neutrons were made of 3 quarks each, later called baryons, while mesons such as pions were composed of a quark and an antiquark. Suddenly the chaos revealed structure. Patterns emerged where before there had been randomness. The hidden order of the universe began to take shape. At roughly the same time, another physicist, George Zweig, proposed a similar model, calling his version ACES. But Gell-Mann's name, and his daring intuition, endured. Yet from the start, there was a glaring issue. If quarks were real, why couldn't we detect one? No experiment had ever isolated a single quark. Whenever scientists tried to break protons apart, nature fought back, generating new quark pairs rather than freeing them. The more energy they applied, the more quarks appeared, but always bound in groups. It was as though the universe refused to show its sleight of hand. This peculiar behavior, later known as confinement, became one of the core principles of the strong nuclear force. But in the early years it cast doubt on quark theory itself. Could something that could never be seen be considered real? Even Gell-Mann hesitated to call quarks physical. He saw them as useful abstractions, conceptual tools to organize chaos. But as experimental methods improved, evidence mounted. In the late 1960s, experiments at the Stanford Linear Accelerator showed that when electrons were fired into protons at high energy, the scattering patterns revealed tiny hard centers inside, consistent with Gell-Mann's quarks. These were dubbed patrons, and their behavior perfectly matched the predicted quark structure. The mystery began to unravel. Over time, new flavors of quarks were discovered: strange, charm, bottom, and top, expanding the family to 6. The strange quark explained unusual decay patterns in kaons. The charm quark was theorized to fix mathematical inconsistencies in weak force interactions and was confirmed in 1974 with the discovery of the J/psi particle. Bottom came next, then the top in 1995, the heaviest of them all, nearly as massive as a gold atom, yet so unstable it vanished in less than a trillionth of a second. Still, none ever appeared alone. No matter how advanced our technology became, quarks refused isolation. They existed only in pairs or triplets, never free. This forced physicists to rethink what existence even means. Are quarks tangible things, or just relationships, patterns, rules written into the universe's grammar? Perhaps they are not particles at all, but mathematical poetry, the syntax of creation itself. Like waves on the ocean, quarks cannot exist apart from the fields that sustain them. Remove the field and the quark vanishes, just as a wave ceases when the sea is gone. And yet, these unseen entities form everything we know. 6 flavors define all matter: up, down, strange, charm, bottom, and top. Each carries unique mass, charge, and behavior, 6 notes in nature's hidden symphony. But only 2, up and down, compose the ordinary world. 2 ups and 1 down make a proton, 2 downs and 1 up form a neutron. This elegant symmetry underlies everything: your body, the stars, the entire cosmos. The rest exist only briefly, fleeting visitors that reveal the deeper complexity of creation before disappearing. So are quarks real? Perhaps not in the way we think of reality, They may be patterns rather than particles, stories rather than things, the most successful fiction nature ever wrote. A whisper in the equations, a secret carved into the structure of existence, unseen yet undeniable. The universe, it seems, was built on ghosts. The enigma of quarks sits at the heart of modern physics, representing both triumph and torment for scientists seeking to understand the universe's smallest constituents. Through decades of experimentation, physicists have mapped quark interactions with extraordinary accuracy. We know how they combine to form protons, neutrons, and other hadrons. We can calculate their confinement inside atomic nuclei and predict the outcomes of high-energy collisions with astonishing precision. And yet, despite this mastery of description, their very origin remains utterly mysterious. The question is no longer how quarks behave. It's why they exist at all. Every aspect of quarks seems deliberately structured, yet no principle in physics mandates their form or function. There are 6 known varieties: up, down, charm, strange, top, and bottom, each with distinct masses, charges, and interactions. These flavors appear arbitrary, scattered across a spectrum of properties that have no deeper explanation. Why not 4? Why not 8? Why do their masses differ by such staggering factors, from the nearly massless up quark to the incredibly heavy top quark? The Standard Model, as successful as it is, offers no hint of why this arrangement exists. It accepts quarks as fundamental and moves on, leaving their reason for being as one of the greatest open questions in physics. What makes this puzzle even more perplexing is that quarks cannot be observed directly. Unlike electrons, which can be isolated and measured, quarks are permanently confined within composite particles. The strong nuclear force, governed by the theory of quantum chromodynamics, QCD, binds them together so tightly that any attempt to separate them results in new particles forming instead. This confinement means that quarks, the supposed building blocks of matter, can never exist independently. We infer their presence from the traces they leave behind, from the jets of particles created in accelerators, or from the energy distributions seen in deep, inelastic scattering experiments. In a sense, we know quarks the way we know black holes, by their effects, not by direct observation. This strange invisibility raises deeper philosophical questions. Are quarks truly real in the physical sense, or are they mathematical constructs, convenient placeholders in our equations that describe something even more fundamental? Some physicists have suggested that quarks may be emergent entities, not fundamental at all, but patterns arising from a deeper level of quantum reality. Others propose they could be manifestations of vibrating strings or excitations in an underlying quantum field, with their properties determined by geometry rather than intrinsic identity. The precision with which quarks fit into the universe adds to the riddle. If their masses or charges were even slightly different, atoms as we know them would not form. The balance between the up and down quarks, for instance, determines the stability of protons and neutrons. Shift that balance, and the fabric of matter collapses. Hydrogen would not exist. Stars could not burn. Life, at least in its present form, would be impossible. This apparent fine-tuning suggests either a deeper organizing principle, something hidden beneath the Standard Model, or an unsettling randomness at the foundation of existence. Adding to the strangeness, quarks are always found in triplets or pairs, never alone. This rule of confinement, though mathematically consistent, feels almost metaphysical. It's as if nature insists on unity at its most fundamental level, binding quarks together so that isolation becomes an impossibility. In this way, quarks seem to embody a principle of cosmic cooperation, that matter itself can only exist through relationship. They cannot be torn apart without creating more of themselves, as if reality resists disconnection. Even their interactions defy conventional logic. The force that holds quarks together, carried by particles called gluons, grows stronger the farther apart the quarks try to move. the exact opposite of gravitational or electromagnetic forces. This phenomenon, known as color confinement, ensures that energy poured into separating quarks eventually produces new ones instead. It's a self-renewing cycle built into the fabric of the strong force, a mechanism that both defines and hides the most fundamental components of matter. The deeper we probe, the stranger the pattern becomes. The 6 flavors of quarks seem arranged in pairs, with each pair representing a generation. The first generation, up and down, makes up the atoms of ordinary matter. The second, charm and strange, exists fleetingly in high-energy reactions. The third, top and bottom, appears for mere instants before decaying. Why should nature build its foundation in such repeating tiers, each heavier and rarer than the last? What governs this hierarchy? Physicists have measured the numbers but cannot yet explain them. Moreover, the symmetry that governs quark behavior suggests the presence of deeper rules that remain hidden. The standard model treats quarks and leptons like electrons and neutrinos as 2 sides of a broader structure, connected by mathematical symmetry groups. Yet those symmetries break in peculiar ways, leading to differences that seem almost arbitrary. Some theorists suspect that quarks are merely fragments of a more unified system, perhaps one described by grand unification theories or by the elusive framework of string theory. Then there's the question of why quarks have color charge, an abstract property unrelated to visible color but essential to how they interact. This threefold charge, red, green, and blue, ensures that combinations of quarks form color-neutral particles. It's a brilliant theoretical invention that works perfectly in practice, yet its deeper origin remains obscure. Why 3 colors? Why not 2 or 4? The number just fits, another example of precision without explanation. Even the top quark, the heaviest of all, adds new layers to the mystery. Its enormous mass, nearly equivalent to an entire gold atom, sets it apart from every other particle in nature. Some researchers believe this could be a clue, that the top quark's weight might reveal how mass itself arises or point toward new physics beyond the standard model. But despite decades of measurements, no clear answer has emerged. In this sense, quarks represent the duality at the heart of scientific exploration. They are known and unknown, measurable yet unseeable, perfectly predictable but philosophically unfathomable. We can calculate their existence to astonishing precision, yet their ultimate nature remains hidden behind the mathematical curtain of quantum field theory. They are both the foundation and the enigma of matter, the scaffolding upon which reality rests, and the puzzle that defies its own explanation. Perhaps then, quarks remind us of something profound, that knowledge does not always dissolve mystery. Sometimes it deepens it. The more precisely we describe their behavior, the more clearly we see the outlines of our own ignorance. Whether quarks are truly fundamental or simply echoes of something deeper, their existence points to a universe that is finely structured yet profoundly mysterious. A cosmos where the smallest pieces of matter whisper of truth still beyond our reach. Among the strangest features of quarks is color. It's not literal color, of course, but a quantum property essential to the strong nuclear force, the very glue holding matter together. Quarks come in 3 colors: red, green, and blue. These are metaphorical, but the concept is vital. For any group of quarks to form a stable particle, their colors must combine into a neutral state, just as red, green, and blue light mix to produce white. This balance is what keeps quarks permanently confined within larger particles. A lone quark can never exist in isolation. Every proton, neutron, or meson obeys this law of color confinement. The strong force demands harmony. No single color can exist alone. In this intricate dance of colors, flavors, and spins, physics reveals the faint outlines of a deeper design, something beyond our full understanding, but impossible to ignore. The 6 quark flavors, up, down, charm, strange, top, and bottom, might be the closest thing humanity has to a universal alphabet of matter.
but it's an alphabet without a Rosetta Stone. Quarks speak a language we can only interpret through their effects, in decays, in scattering patterns, in the subatomic poetry of mass and charge. They remind us that beneath every scientific answer lies another question, and that even the smallest pieces of reality are profoundly strange.
We trust in quarks. We calculate their properties, use them to predict reactions, and confirm those predictions with breathtaking precision. Yet, no one has ever seen a quark. Not through any microscope, not in any particle collider. They cannot be isolated, observed in motion, or even captured at the instant of their creation. Every quark ever detected has lived and died bound to others, never free, never solitary. This isn't a technological limitation, it's a law of the universe itself, buried deep in quantum chromodynamics, QCD, the theory describing how quarks behave. This law is called confinement. Imagine stretching a rubber band, pull the ends apart, and the tension increases. Now imagine that same principle applied to space itself. When two quarks are pulled apart, the strong force between them doesn't weaken like gravity or electromagnetism, it strengthens. The farther apart they get, the more desperately the force pulls them back. Eventually, the energy stored in that tension becomes so immense that it transforms into matter, spawning new quark-antiquark pairs from the vacuum itself. You can't separate quarks. You only end up creating more. Nature refuses solitude. This principle overturns our classical view of matter. We once believed that if we kept dividing objects, we'd eventually find an indivisible core, a final solid piece of everything. Quarks shattered that illusion. They are not tiny marbles or building blocks. In quantum field theory, particles are not objects at all. They're disturbances in invisible fields that fill all of space. Each particle type corresponds to its own field, the electron field, the photon field, the Higgs field, and of course the quark fields. A quark then isn't a physical thing but a vibration, a fleeting fluctuation in a vast omnipresent field. Unlike electrons or photons, these vibrations can't exist freely. They're tied together by the gluon field, the medium of the strong force. Gluons, like photons, carry force, but unlike photons, they also interact with one another, forming complex, tangled webs of energy. Within these webs, quarks are trapped forever, confined like marbles, knotted inside a net made of pure force. That's why no one has ever seen a quark. It's not meant to be seen. A quark exists only as part of a system, one voice in a cosmic harmony that cannot be sung alone, and yet we know they exist, not through direct observation, but through their unmistakable footprints. When protons collide at near light speed, the debris they leave behind forms distinct patterns, energy jets, resonance peaks, angular signatures, all pointing to something hidden within. We infer quarks' existence from these shadows, much like the figures on the wall in Plato's cave. But this raises a deeper question. If a quark can never exist alone, is it truly real? Does real mean something we can touch and see, or something we must believe in because the equations demand it? Many fundamental entities in physics, gluons, gravitons, even dark matter, are known only by their effects. Some physicists argue quarks are not objects at all, but convenient mathematical constructs like negative numbers, tools that make the equations work. Others believe our instruments are simply too crude, and that one day, with enough precision, we might glimpse a quark in isolation. Yet even the most violent collisions humanity has ever created show the same outcome: confinement. Quarks appear only in groups, never alone, so we adjust. We study not the particles themselves, but the jets of energy they leave behind, the echoes of their existence. Ultimately, a quark isn't a bead of matter. It's a ripple in an invisible field, a vibration woven into the structure of reality. It is not meant to be seen, only to be obeyed. And in that obedience lies the true order of the universe, where everything, even the smallest piece of existence, is part of a grand, inseparable whole. The universe as we know it could not exist without quarks. Without them, atoms would never bind together, the periodic table would crumble, and chemistry itself would cease to function. Quark fields are not merely elements within the universe, they are the foundation upon which existence itself rests. They are the invisible framework that allows matter to manifest. This is why we never observe a lone quark. A single quark cannot exist in isolation, any more than a crest can exist without a wave or a note without a melody. Its existence is defined only within a structure, within resonance, within relationship. A quark's meaning lies in connection. Its identity arises only when it interacts with other quarks, other fields, other forces. But fields alone are dormant. They need disturbance, a ripple, an excitation that gives rise to the phenomena we perceive as particles. Those ripples, temporary vibrations of the field, become the building blocks of matter. Quarks are among those ripples, fleeting yet fundamental. Without them, there would be no atoms, no stars, no structure, and no consciousness to question it all. They are not just particles, they are manifestations of a deeper relational pattern that defines reality itself. At the most fundamental level, the universe is not built from things but from interactions. What we perceive as substance is really the dynamic relationship between invisible forces that create tension, balance, and symmetry. Quarks are the visible echoes of those unseen interactions, the earliest ripples in an infinite web of connections stretching across space and time. This understanding brings us to one of the most profound discoveries in modern physics, quantum entanglement. There exists a story written in silence, a story of two particles born together that remain connected no matter how far apart they drift. They act as one, defying distance, time, and even the speed of light. This is not fantasy, it is the strange reality confirmed by quantum mechanics. And now, for the first time, entanglement has been observed at the most fundamental level, within quarks themselves. In a subterranean ring beneath Geneva, scientists at the Large Hadron Collider, LHC, discovered evidence of entanglement in top quarks, the heaviest and rarest of all quark types. This finding redefines what we know about matter and reality. Until now, entanglement had only been confirmed in photons and electrons. To observe it in quarks means that even the basic fabric of matter, the particles that make up protons and neutrons, can exist as part of a shared quantum state. Quantum entanglement stands as one of the most bewildering and revolutionary concepts in modern physics. It questions the very foundations of how we understand cause, effect, and the limits of space and time. At its core, entanglement describes a state in which two or more particles share a connection so deep that their properties become inseparable, even when they are separated by vast distances. What happens to one instantly influences the other, not through a signal, not through any exchange of energy, but through a shared quantum state that transcends classical boundaries. When two particles become entangled, they essentially lose their individual identities. Instead of being described separately, they must be treated as one system governed by a single mathematical expression, a shared wave function. This is why physicists often say that entangled particles are not two independent entities, but rather one equation existing in multiple locations. If you measure the spin, polarization, or charge of one particle, the other's corresponding property is determined at that very instant, no matter how far apart they are. This immediate coordination violates what Einstein called locality, the idea that an object can only be influenced by its immediate surroundings. In the classical world, everything follows locality. A billiard ball moves only when another ball strikes it. A planet orbits due to the gravitational pull of a nearby star. But in the quantum world, such neat separations collapse. Einstein, Podolsky, and Rosen highlighted this problem in 1935 through the famous EPR paradox. They argued that quantum mechanics must be incomplete because it allowed what seemed like instantaneous influences across space, what Einstein derisively called spooky action at a distance. To preserve realism and locality, Einstein proposed that hidden variables might exist, unseen factors that predetermined the outcomes of measurements. If such hidden variables were real, then the weirdness of entanglement could simply be explained as ignorance on our part, rather than a breakdown of causality. However, the decades that followed brought experiments that slowly dismantled this comforting idea. In the 1960s, physicist John Bell devised a mathematical inequality, now called Bell's theorem, that allowed scientists to test whether hidden variables could explain quantum correlations. When the experiments were finally performed in the 1970s, 1980s, and more conclusively in the 21st century, the results were clear. Nature violates Bell's inequalities. In other words, no hidden variables can fully account for what happens. The universe truly behaves in a non-local way at the quantum level. This means that entanglement is not an illusion or a theoretical trick. It's a fundamental feature of reality. Two particles that have interacted once can remain connected forever, sharing a bond that transcends distance. What's even more astonishing is that there's no way to use this connection to transmit information faster than light, because each measurement still appears random until compared later. The instantaneous link doesn't carry a message. It reveals correlation, not communication. Yet it proves that the classical notion of separate, isolated systems does not apply at the smallest scales of nature. For decades, this phenomenon remained mostly a philosophical puzzle. But now, with the advancements in experimental technology, particularly through colliders, quantum computers, and high-energy detectors, entanglement has become a measurable, exploitable resource. The Large Hadron Collider, LHC, the most powerful particle accelerator ever built, has brought the study of entanglement to the subatomic frontier. Its detectors have revealed patterns that suggest even quarks, the fundamental constituents of protons and neutrons, can exhibit quantum entanglement. This is a profound discovery because it implies that entanglement isn't limited to photons or electrons, which are often used in quantum optics experiments. Instead, it extends to the very particles that form the core of atoms. When two protons collide at nearly the speed of light, their internal quarks and gluons interact in ways that produce deeply correlated outcomes. By analyzing these correlations, physicists have found evidence that the behavior of one quark is instantly reflected in its partner, even when separated across measurable distances. This suggests that entanglement might be a fundamental thread woven through all matter, not an exception but a universal rule. Understanding entanglement at this level could revolutionize our comprehension of the universe's structure. For one, it may reveal that what we perceive as distinct particles are actually expressions of a unified quantum field. If everything is connected through entanglement, then separateness is merely an illusion created by limited observation. In this view, the entire cosmos could be seen as one vast quantum system, a seamless fabric where every particle resonates with every other. This realization has deep implications for both physics and philosophy. It means that cause and effect, as we traditionally understand them, might not be fundamental laws but emergent patterns arising from a deeper, non-local reality. Events we see as separate could, in fact, be different facets of the same underlying process. Entanglement thus bridges the gap between what we call space and information, showing that knowledge of one system can instantaneously define another, regardless of spatial separation. The confirmation of entanglement in matter particles also strengthens the ongoing effort to unify quantum mechanics and general relativity. Einstein's equations describe gravity as the curvature of spacetime, while quantum theory governs the behavior of particles at microscopic scales. For decades, these two frameworks have refused to merge, but entanglement may be the key. Some researchers propose that the very geometry of spacetime might emerge from quantum entanglement itself. In other words, the fabric of space could be nothing more than a web of entangled relationships, the universe's way of maintaining coherence and structure. If this turns out to be true, then entanglement isn't just a property of particles. It's the mechanism that holds the cosmos together. Every atom, star, and galaxy might exist because quantum information remains consistently linked across the universe. This would mean that distance is not a barrier, but a construct, a byproduct of how entangled systems appear when viewed through classical eyes. What we interpret as space could be a projection of invisible quantum relationships woven at the deepest level of existence. Moreover, this understanding is not purely theoretical. Quantum entanglement is already being used in practical technologies. Quantum computers harness entangled states to perform calculations that would take classical machines centuries to complete. Quantum encryption uses entanglement's inherent unpredictability to create communication channels that are fundamentally secure. And future quantum networks, sometimes referred to as the quantum internet, aim to transmit entangled particles across global distances, allowing instant coordination of quantum systems worldwide. These applications not only prove entanglement's reality, but also show that it can be manipulated and engineered. Yet, even as technology races ahead, the mystery remains. What does it truly mean for two objects to share a single quantum state? If one measurement affects another instantly, does that imply information travels outside spacetime? Or does spacetime itself expand to include both particles as one? The answers remain elusive. But every new experiment brings us closer to understanding that entanglement is not a glitch in physics. It is physics itself. The latest findings from the LHC reinforce this idea by showing that entanglement occurs naturally among the building blocks of all visible matter. This means that everything we see, every rock, atom, and cell, is the end result of quantum relationships stretching back to the dawn of the universe. The interactions that shaped the first protons and neutrons after the Big Bang may still echo through entanglement today. In this sense, entanglement is the language of creation, a silent code that connects all things. It challenges our assumption that separation is real and suggests that, at the deepest level, the universe is one continuous entity observing itself through countless quantum mirrors. We are not just made of matter, we are made of relationships, entangled across space, across time, and across the unseen fabric that binds reality together. The ATLAS collaboration at CERN achieved this discovery by analyzing the data from high-energy proton collisions. These collisions create pairs of top quarks and top antiquarks that emerge together from the violent energy of impact. Because the top quark is incredibly massive and unstable, it decays almost instantly before it can bind to other quarks. Unlike most quarks, it doesn't form protons or neutrons. It dies bare, leaving behind a trail of decay fragments that physicists can measure. When the researchers studied these decay products, they noticed a distinct pattern. The spins of the top quark and its antiporter were not random. They were correlated, aligned in a way that could only be explained by quantum entanglement. Despite traveling in opposite directions at nearly the speed of light, these quarks behaved as if they were still part of the same entity. Their brief existence, measured in trillionths of a second, revealed something astonishing. Even as they disintegrated, their quantum state remained unified. This discovery implies that the universe does not merely hold particles together, it preserves relationships. What defines reality is not where a particle exists, but how it is connected to everything else. If quarks, the most fundamental ingredients of matter, can be entangled, then individuality itself may be an illusion. Every atom, every cell, every being could be part of a vast interconnected system, a cosmic equation unfolding across space-time. Entanglement tells us that nothing exists in isolation. The quarks in your body may share invisible bonds with quarks scattered across the universe. Every action, every fluctuation might echo in distant corners of existence. The idea of separateness begins to dissolve, replaced by a deeper unity. A universe made not of parts but of patterns, each reflecting the other in perfect symmetry. And if this connection is real at the smallest level, what does it mean for us? It suggests that even the particles composing your body are not truly yours. They are fragments of a universal web of relations, temporary configurations in a shared field of being. Entanglement reveals that the universe is not built from independent objects, but from relationships that span infinity. The revelation that quarks can be entangled forces us to rethink the nature of matter itself. Perhaps particles are not permanent objects at all, but fleeting events, moments when the universe briefly becomes self-aware of its own structure. Perhaps what we call a quark is not a particle, but an event in space-time, a note in the ongoing music of creation. To understand this, we must travel back to the very beginning, before atoms, before stars, before structure, when the universe was pure energy. In that first instant after the Big Bang, there existed a state known as quark-gluon plasma, a seething, formless ocean where quarks and gluons drifted freely, unbound by the forces that now confine them. For a few fleeting microseconds, it was the natural state of existence, a perfect fluid of pure freedom and symmetry. As the universe expanded and cooled, this plasma condensed. The strong nuclear force trapped quarks into hadrons, giving rise to protons, neutrons, and all subsequent forms of matter. The chaos didn't vanish. It crystallized into structure. The universe froze into order, and from that cooling came everything that exists. But scientists have learned to recreate that first moment. At the relativistic heavy ion collider, RHIC, in New York, gold nuclei are accelerated to near light speeds and smashed together, creating temperatures hotter than the core of a supernova, over 4 trillion degrees Celsius. For an instant, the quark-gluon plasma returns. It behaves not as chaos, but as an astonishingly smooth liquid, a perfect fluid, more unified than anything else in nature. This state challenges every assumption. The plasma flows as one, without friction, without boundaries. It suggests that the original state of the universe was not disorder, but unity. Before confinement, before separation, before the emergence of form, there was coherence. So why did it end? Why did quarks lose their freedom? As space cooled, the gluon field strengthened, binding quarks into stable combinations. Freedom became structure. The plasma of potential turned into the geometry of matter. In that transformation lies the story of everything, from chaos to cosmos, from energy to life. And yet the memory of that original state remains within us. Every proton in your body carries the echo of that first plasma, locked inside the quarks, yearning to move freely again. You are, quite literally, the residue of cooling, the solidified trace of a universe that once flowed like a perfect liquid. Strip away all matter, and what remains is not emptiness, but restless energy. The vacuum itself hums with potential, vibrating with virtual particles that flicker in and out of existence. Even nothing is alive with motion. The universe, at every scale, is not made of static pieces, but of constant relationships, of vibrations, of energy exchanging itself endlessly. And so we return to the question, are quarks even real? Perhaps not as things, but as interactions, not as objects, but as moments of harmony in the eternal music of the cosmos. Every event in the universe exists within a larger context. Every particle is woven into an unseen tapestry of possibilities, surrounded by the ghosts of what could be. When physicists model a quark using quantum chromodynamics, they do not describe a solid, fixed point in space. They describe a cloud, a swirling field of probabilities, a storm of constant creation and annihilation. Within this chaotic mist, real quarks, virtual quarks, gluons and antiquarks appear and vanish, colliding and recombining endlessly. The vacuum of space isn't empty. It is alive, an active participant. It interacts with the quark, shaping and restraining it, enclosing it within invisible mirrors. This makes the phenomenon of confinement all the more fascinating. The vacuum, if left undisturbed, would prefer freedom. It would allow quarks to drift apart. Yet the strong nuclear force resists this. It holds the quarks tightly together, pulling with increasing strength the farther they try to move apart. It's as if space itself refuses to let them go. When one quark is forced away, the vacuum doesn't release it. It creates new quarks from its own energy to preserve the balance. Thus, when physicists say quarks are confined, they mean that these particles exist within a constant struggle, trapped between the binding rules of force and the restless turbulence of nothingness itself. And perhaps the greatest irony lies in the vacuum itself. The very emptiness that seems to separate all things might actually define what quarks are. Some speculative theories propose that quarks aren't truly fundamental particles at all, but rather stable knots within the quantum field, self-sustaining ripples in the vacuum's fluctuations known as solitons. If this is true, then quarks aren't the beginning of matter, but the result of something even deeper. A vacuum capable of structuring itself, of organizing chaos into coherence. In this sense, nothingness might not be empty at all, but intelligent, a self-aware field capable of giving birth to everything, including gravity itself. Even mass, the defining property of matter, may not belong to particles inherently. The Higgs field, which gives particles their mass, could simply be responding to the restless churn of the quantum vacuum. What we perceive as a particle may be no more than a momentary interruption, a point where the vacuum stumbles and creates a temporary bubble of tension, a localized knot in the flow of space-time. These bubbles join together to form protons. Protons unite to form nuclei. Nuclei gather into atoms, and from those atoms, stars and galaxies are born. And within that chain of creation, from vacuum to energy to matter, emerged life itself, you. You are a being made not of permanence, but of motion, a pattern of quarks and energy bound together just long enough to give the illusion of solidity. Every atom in your body, every proton in your veins, is a miniature universe of restless motion. The particles that compose you do not sit still. They vibrate, flicker, and exchange forces in an eternal, invisible dance. Their interactions sustain the shape you call you, but that shape is only temporary, a momentary pause in an infinite sea of quantum turbulence. At the heart of your existence lies a paradox. Everything that makes you tangible originates in something intangible. The quarks forming your body are confined within protons and neutrons, bound by the strongest force known to physics, a force so fierce that it refuses to let any quark exist alone. And yet, despite their invisibility, their collective activity gives rise to all that is visible. You are therefore a being composed of unseen events, the physical embodiment of interactions that have never stood still long enough to be observed directly. This storm of activity occurs within a framework known as the quantum vacuum, a state we once mistook for emptiness, but which modern physics now understands to be teeming with activity. Even in the absence of matter, the vacuum hums with energy. Virtual particles appear and vanish in infinitesimal instants, their brief existence shaping the properties of the universe. It is from this restless field that all structure arises. The quarks that form you are not static things dropped into space. They are disturbances of this field, small flashes of order within an endless background of possibility. When you breathe, when you think, when you simply exist, you are not distinct from this vacuum. You are part of it. The atoms of your body are not foreign entities suspended in space. They are space, organized into a fleeting configuration of stability. Reality in this sense is self-organizing energy. The universe arranges itself into patterns that temporarily resist entropy, giving rise to stars, planets, and consciousness. And you, with your memories and perceptions, are one such configuration, a brief triumph of coherence against the background noise of chaos. It's tempting to think of chaos as the opposite of order, but in quantum terms, chaos is the raw material of creation. The unpredictable fluctuations of the vacuum are not meaningless. They are the source from which order emerges. Every quark in your body, every photon that strikes your eyes, is a product of these fluctuations stabilized by the laws of physics. What we call matter is simply energy that has slowed down, folded upon itself, and found equilibrium. You are not separate from that process. You are that process, momentarily self-aware. Your very awareness is built upon this paradox. The neurons in your brain function through the exchange of ions, tiny charged particles that obey the same quantum laws as quarks. Each thought is a cascade of electrical interactions, a fleeting pattern of organized motion. Yet within that motion, consciousness arises, something abstract, unmeasurable, and yet undeniably real. How can awareness emerge from a collection of non-conscious parts? Perhaps because the universe itself is structured in such a way that organization leads to reflection, that the same patterns of coherence that hold atoms together can also generate the phenomenon of thought. In that sense, you are not merely observing the universe, you are the universe observing itself. Your thoughts, emotions, and perceptions are not external to the cosmos, but expressions of it. You are the temporary focus of an ancient process, a pattern refined by time, shaped by chance, and guided by laws we are only beginning to grasp. The particles composing you were forged in the heart of stars billions of years ago, scattered through supernova, and later gathered into this form that now asks questions about its own origin. You are not apart from the stars. You are their echo, their continuation, their memory written in biological form. The you that perceives, however, is not fixed. Your body replaces its atoms constantly. The quarks forming your matter today are not the same ones that made you yesterday. Yet your sense of identity persists, suggesting that the essence of being lies not in matter itself, but in the pattern it holds. Like a flame sustained by continuous combustion, you endure through change. You are the shape of motion, not the content of it. Think of yourself as a ripple, a temporary coherence in an otherwise restless medium. Waves on water do not travel as matter. They are patterns of movement through the liquid. Likewise, you are a wave traveling through the quantum fields of reality, your physical structure a standing pattern that temporarily maintains its form. When the energy that sustains it disperses, the pattern fades, and what you call you dissolves back into the sea of potential. And yet, this dissolution is not destruction. In quantum physics, energy is never lost and it only transforms. The quarks that form your body will outlive you, recombining into new atoms, new stars, new beings. You are in every sense immortal, not as an individual, but as a process. The universe forgets your shape but remembers your essence. The energy that once fueled your consciousness will reappear elsewhere, reshaped by time into a new story. The mystery of your existence deepens when you realize that even the void you return to is not truly empty. Space itself is active, pregnant with fields and fluctuations that birth reality anew at every instant. The vacuum is a creative force, a kind of cosmic mind that dreams in energy rather than words. Every event that occurs, from the flicker of a quark to the birth of a galaxy, is an expression of that dream. If consciousness arises from the universe, then perhaps the universe itself is a form of consciousness, vast, impersonal, but alive in its own way. In that grand picture, you are a fleeting thought within the universal mind, a temporary reflection of its ongoing meditation on itself. The atoms that compose you were once parts of countless other beings. The light that strikes your eyes has traveled billions of years to arrive. You are a continuation of everything that has ever been, condensed into a single, momentary awareness. The cosmos remembers itself through you, even if only for a breath. And just as quickly as you arise, you dissolve. The thought fades, but the ocean remains. The quarks that define you merge back into the ever-shifting sea of fields and forces, waiting for another configuration to call them into being. Existence, it seems, is a continuous act of remembering and forgetting, the universe thinking itself into form, then letting that form go. So when we ask, are quarks even real? We must also ask, is the vacuum real? Because beneath every proton, beneath every atom, beneath every physical law lies something restless, something that never stops moving, never stops creating. The vacuum is not empty, it is not silent, it is not done. It is an eternal pulse, a quantum breath that stretches through infinity, within which quarks are born again and again, endlessly. For most of modern physics, reality seemed simple. Quarks combined neatly into twos or threes. Three quarks formed baryons, such as protons and neutrons. Two, a quark and an antiquark, formed mesons, like the fleeting pions that appear during nuclear reactions. It was an elegant system, perfectly ordered, but the universe, as always, refused simplicity. In 2003, physicists in Japan and China discovered something that defied the textbooks, a new kind of particle, temporary but unmistakably real. It wasn't a baryon or a meson. It was something new, the Z, 3900, composed of four quarks, a charm quark, an anti-charm, an up, and an anti-down. This particle didn't fit the established model. It was a tetraquark, and it opened the door to an entire world of exotic matter. Since then, dozens of tetraquark candidates have been detected, each with unique properties. Some involve bottom quarks, others strange or charm combinations. Some behave like molecules, two mesons orbiting each other in a fragile dance, while others are compact, with four quarks packed tightly together, sharing gluons within a dense quantum cage. Still others form diquark-centered states, displaying symmetry reminiscent of helium atoms. Each type interacts differently with forces and decays along its own distinct path, yet all follow the same underlying rules of confinement, color charge, and quantum stability. The discovery of tetraquarks revealed something profound. The strong force, the fundamental glue that binds matter, is far more versatile than we ever imagined. It doesn't merely stick particles together, it weaves them into new patterns, new grammars of existence. In 2021, CERN's LICE experiment confirmed the existence of T3875, the first doubly heavy tetraquark with unpaired open-flavor quarks. This discovery confirmed that heavier, more complex quark combinations could exist, not just as mathematical predictions, but as physical reality. If four quarks can unite, why not five? Why not six? Indeed, physicists have since discovered the pentaquark, five quarks bonded together, and are now studying possible hexaquark configurations. Each discovery reshapes our understanding of what matter can be. The strong force is not limited to binding triplets or pairs. It's an infinite artist, sculpting new configurations of matter under the right conditions. And this creativity doesn't end at the microscopic level. Some theories propose that under extreme pressure, such as in the core of a collapsing neutron star, quarks could break free from confinement and flow as a single, continuous fluid of quark matter. These hypothetical quark stars, denser than any known object, may already exist in deep space, their strange signatures defying neutron star models. If true, the implications are staggering. Multi-quark matter may not just exist in particle accelerators, it could shape the very structure of the cosmos. Some physicists even suggest that the early universe produced quark nuggets, stable chunks of quark matter left over from the Big Bang, now drifting invisibly through the cosmos as candidates for dark matter. All of this leads to a breathtaking realization. Quarks are not merely the building blocks of matter. They are expressions of potential, permissions granted by the universe's laws of possibility. The deeper we look, the clearer it becomes. The subatomic world is not a tidy foundation, but a wilderness of relationships, a boundless ocean of becoming. We once thought matter was composed of atoms. Then we discovered protons and neutrons, then quarks. Now we are learning what quarks themselves can become, how they combine, how they change, how they evolve. Reality, it seems, is not a collection of fixed parts, but a dynamic process of emergence. And so we arrive again at the same question. Are quarks even real? Perhaps not as solid particles, but as fleeting events, self-sustaining ripples in the fabric of existence. Perhaps they are not things at all, but moments of harmony in the eternal vibration of the universe, temporary notes in a song that never ends. Are we truly surrounded by forms that only appear stable, shapes that feel solid beneath our hands, yet are, in truth, dynamic events unfolding every instant? The deeper science peers into the fabric of existence, the more it seems that permanence itself is an illusion. The chair beneath you, the air you breathe, even the atoms composing your body, none are static. They are not fixed objects but temporary symphonies of energy, sustained by ceaseless motion and fluctuation. When viewed through the lens of quantum mechanics, reality becomes a choreography of patterns rather than a collection of parts. This realization invites profound questions. Could consciousness itself be one of these patterns? Perhaps awareness is not a thing we have, but a rhythm we are, a coordinated vibration of neural and quantum interactions that gives rise to the experience of self. In this view, memory would not be a substance stored in the brain like ink on a page, but a recurrence of specific configurations, an echo that replays within a vast and ever-changing field of electrical impulses. The sense of continuity that defines identity might simply be the universe performing a familiar tune in different moments, each repetition a slightly altered version of the last. Quantum physics supports this notion of a reality built on rhythm and recurrence rather than material permanence. At the subatomic scale, no object maintains a stable identity for long. Particles emerge from quantum fields, exist for a fleeting instant, and then fade. They interact, transform, or decay into other forms, driven by probabilities rather than deterministic laws. Even the so-called fundamental components, like electrons or quarks, are not fixed entities. They are expressions of underlying processes, localized events within an ever-fluctuating field. The more precisely scientists measure their properties, the more apparent it becomes that these particles are not self-contained objects, but dynamic nodes of interaction. Time itself may belong to the same category, a construct emerging from the relationships between processes rather than an independent backdrop. In classical physics, time was treated as an absolute and invisible stage upon which the universe unfolded. But quantum theory suggests that time could be born from change, not the other way around. Each interaction, each exchange of energy defines a before and after, and from this accumulation of transitions arises what we perceive as the flow of time. Without motion, there is no temporal sequence, only still potential. Thus, time may not exist at the deepest level. It could be a phenomenon woven by the universe's own internal dance. This brings us to the strange and elusive behavior of quarks, the very ingredients of the visible world. These minute entities form the protons and neutrons inside atomic nuclei, the stable foundation upon which all matter depends. Yet the quarks themselves are anything but stable. They flicker between states, bound together by an invisible force so strong that it prevents them from ever being observed in isolation. In laboratories, no one has ever seen a single quark alone. Instead, what we observe are their effects, jets of particles produced when quarks momentarily reveal their existence before merging again into new combinations. This peculiar existence, always confined, never separate, positions quarks precisely on the edge between being and becoming. They are real enough to construct the universe, yet intangible enough to defy direct observation. Their reality depends not on their individuality, but on their relationships with each other, on the way they interact within the sea of gluons that binds them together. This is why physicists often describe them not as particles in space, but as excitations of a deeper quantum field, temporary disturbances that create the illusion of form. What makes quarks particularly fascinating is how their behavior mirrors the tension between permanence and change that defines reality itself. They are born out of pure energy when conditions allow, briefly exist as recognizable entities, then vanish or recombine, leaving behind only the results of their interactions. This transient dance ensures the stability of matter at large scales, even though instability rules the microscopic realm. It's a paradox that lies at the heart of existence. The universe's enduring structures, mountains, stars, organisms, are built from components that never stop fluctuating. Such a perspective reshapes our understanding of what it means for something to exist. In the classical worldview, to exist meant to occupy space and persist through time. But in the quantum world, existence is a spectrum of probabilities. Things exist only when conditions force them to. Until measured or interacted with, they remain potentialities rather than actualities. This principle, known as superposition, implies that even reality itself may be undecided until observed. The act of interaction, whether through measurement, observation, or entanglement, collapses that field of potential into a specific outcome. Reality, then, might be less a collection of things and more an ever-evolving conversation between possibility and realization. Quarks embody this quantum paradox perfectly. They are necessary for the existence of the physical world, yet they do not exist in the ordinary sense. Their individuality dissolves into a web of interactions, their boundaries defined only by the energy that holds them in balance. They act as though they are real, creating structure, mass, and stability, while remaining invisible and intangible. The world we inhabit depends on their behavior, but their true nature remains hidden beneath layers of probability and mathematical abstraction.
When seen this way, the distinction between physics and philosophy begins to blur. What we perceive as solid, stable, and enduring may simply be temporary coherence within a universe that is fundamentally fluid. Even consciousness might be one of these fleeting coherences, a self-organizing pattern arising from the same field of quantum energy that gives rise to matter. The human experience, then, becomes another expression of the universe's unfolding, another manifestation of the endless interplay between order and chaos.
In this light, asking whether quarks are real becomes less about discovering a definitive answer and more about understanding the language of existence. Their reality is not defined by visibility or tangibility, but by necessity, the fact that their behavior explains everything else. They do not need to be seen to shape the cosmos. Like the pulse of time, the spark of thought, or the emotion that moves the human heart, their presence is felt through their effects. Perhaps in the end, the universe itself operates on this principle. The most fundamental aspects of existence are not the things we can touch or see, but the patterns that persist through change. Quarks, consciousness, and time all share this quality. They are processes, not possessions. They emerge, perform their function, and dissolve, leaving behind traces that guide the next cycle. And in that endless rhythm of appearance and disappearance, of formation and transformation, lies the true heartbeat of reality, a cosmos not built from things, but from the eternal act of becoming.
Despite this constant flux, quarks display remarkable consistency. They obey the same laws, decay predictably, and follow strict conservation principles. They construct protons and neutrons, which in turn form atoms, matter, and ultimately life itself. So, if quarks are not tangible things, why do they behave with such reliability? Perhaps because what we call reality is not made of objects at all, but of repeating patterns. Imagine a wave rolling across the ocean. You can point at it, surf it, even photograph it, but you cannot contain it. You can only capture its form for a fleeting moment, not its essence. The wave is not the water itself. It is the pattern the water temporarily assumes.
Quarks may function in a similar way, as the universe's version of a wave taking form within a field. They represent moments of order emerging from underlying chaos. and those moments of stability are what we interpret as particles. This explains why quarks can never be observed in isolation, and why they only exist as part of larger structures. Their properties arise through interaction, not independence. Even their masses, so different and puzzling, may depend on the energy fields in which they form, much like how the same song sounds different on various instruments. In that sense, quarks are context-sensitive. They become whatever the universe requires, wherever and whenever it needs them. They are not just the foundation of matter, but the flexibility that allows the universe to change, adapt, and reconfigure itself into new states of being.
This redefines how we think about existence itself. We've been trained to think in terms of nouns: proton, electron, atom, human. But perhaps the universe is written in verbs: vibrate, combine, collapse, radiate, transform. Maybe a quark is not a thing at all, but an action, a recurring movement of reality that stabilizes just long enough to be recognized before shifting again. This explains why protons endure for billions of years while top quarks disappear almost instantly. Each quark is a flicker of existence, a pulse of possibility that briefly stabilizes just long enough to matter before dissolving again into the quantum field. So when we ask whether quarks are real, we might be asking the wrong question. Maybe reality itself is not a set of things, but a continual act of emergence, a cosmic process that keeps discovering itself. Quarks could be that process in motion, not the endpoint of physics, but the universe's way of speaking, a syllable repeated endlessly, whispering, continue, evolve, become. The deeper we probe into the quantum realm, the more it feels like we're not observing what is, but what could be. Everything that feels tangible, the ground, your body, your breath, is in truth a statistical mirage, a dense cloud of probabilities that for a brief moment coalesce into something recognizable. What we call you, the body, the mind, the self, is not made of solid, unchanging material. It is instead a fleeting structure built out of endless quantum processes. Every heartbeat, every breath, every thought is the temporary outcome of countless subatomic events balancing on the edge between chaos and order. You're not a fixed object in space. You are a living arrangement of probabilities, an organized fluctuation that the universe has momentarily stabilized into form. Beneath the skin, beneath the atoms, everything that feels real arises from phenomena that are never still, waves that continuously create and dissolve structure faster than any eye could see. At the very center of this invisible machinery lie the quarks, the smallest known components of matter. They are not solid bits of substance, but dynamic excitations of energy fields. Though we cannot observe a quark in isolation, their presence is inferred from the patterns they leave behind, the energy traces, the interactions, the measurable effects they produce. Quarks are the architects of the physical world. They combine to form protons and neutrons, which in turn assemble into atomic nuclei, the foundation upon which all matter rests. Without them, there would be no atoms, no chemistry, no structure for life to arise within. They are the hidden engines that give substance its strength and coherence. What makes quarks extraordinary is their dual nature. They seem to exist both as entities and as relationships. A quark alone is meaningless. It cannot exist outside of the bonds it forms with others. Inside a proton, for instance, 3 quarks are bound together so tightly by the strong nuclear force that trying to separate them only creates more quarks. Their confinement ensures that reality as we know it never falls apart. This binding gives matter its resistance, the reason your hand cannot pass through a wall, the reason pressure and solidity exist. The strength of that invisible interaction is the reason the physical world feels dependable, even though its foundation is a realm of restless uncertainty. Yet quarks do not behave like classical objects. Their identity changes depending on what interacts with them. In the quantum world, the properties of a system, such as spin, position, and momentum, do not pre-exist measurement.
They emerge through interaction. Until a quark participates in an event, those attributes remain in a state of superposition, many possibilities existing simultaneously. It is as if each quark carries an infinite set of potential states, waiting for an encounter with another particle or a measuring device to choose one. That moment of choice is what physicists call quantum decoherence, the process through which uncertainty collapses into a definite reality. Decoherence is not just a technical detail, it is the mechanism that translates the fluid quantum realm into the tangible world we perceive. Before decoherence, reality is a haze of probabilities, an abstract landscape of what could be. After decoherence, we see a definite state, a specific event, a measurable position, a single fact. Every time light reflects from your skin, every time you touch something or see something, countless decoherence events are taking place at once. They turn potential into presence, possibility into form. This means that everything you perceive, from the solidity of a rock to the warmth of sunlight, is not inherent in matter itself. It is born in the interaction between fields, between particles, between observer and observed. The quarks inside you behave the way they do not because of what they are, but because of what they encounter. Their existence depends on context, on relationships rather than individuality. Each one is a brief intersection of forces, a flicker in the fabric of the cosmos that persists only as long as the pattern holds. Imagine standing before an endless ocean, its surface alive with motion, waves rising, folding and dissolving back into the depths. Each wave seems distinct, yet none truly exists apart from the ocean itself. You can describe its height, speed and rhythm, but once you try to isolate it, the illusion fades. The wave was never a separate object. It was an expression of the ocean's energy, a momentary pattern of motion. In the same way, quarks are not standalone particles but ripples within the deeper quantum field that permeates all of reality. They exist only as excitations of that field, brief, localized events where the hidden fabric of the universe becomes perceptible for an instant. This view challenges our most basic assumptions about matter. We tend to think of particles as solid, indivisible points, the ultimate building blocks of existence. But at the quantum level, solidity disappears. What we call a quark is more accurately a vibration in an invisible medium, one that underlies all space and time. This field is constant, extending everywhere, even in what we consider a vacuum. When energy condenses in specific ways within it, the result is a particle, a quark, a gluon, or any other fundamental constituent of matter. These particles flicker into being not as static entities, but as patterns of resonance, much like how waves emerge and fade within the sea. The implications are profound. If quarks are not truly objects, then the universe itself is not made of things, but of processes. Existence, at its core, is dynamic, a continuous act of creation sustained by the interplay of energy and field. The quarks that give rise to protons and neutrons, and therefore to every atom, are simply stable configurations of these quantum vibrations. Their apparent permanence is an illusion, born from the persistence of pattern, not from the endurance of substance. Like a wave repeating its rhythm across the tide, quarks maintain structure through balance and interaction rather than through solidity. This understanding also explains why quarks cannot exist independently. Just as you cannot scoop a wave from the ocean without taking the ocean itself, you cannot isolate a quark without invoking the entire quantum field it belongs to. The strong force that binds quarks together grows more powerful the further they are pulled apart, ensuring that they remain part of a collective. Attempts to separate them only generate new quarks, new waves in the same boundless sea. This property, known as confinement, reflects the universe's refusal to allow its most fundamental expressions to stand alone. In essence, quarks are moments of order within a field of infinite potential, temporary condensations of energy that make reality tangible. They blur the line between existence and emergence, between being and becoming. Just as no wave can exist without the ocean, no quark exists without the field that sustains it. The universe, therefore, is not built from isolated particles, but from the continuous dance of energy taking form, dissolving and reforming again, a cosmic ocean forever in motion, where every ripple, however brief, carries the signature of eternity. This constant creation and dissolution reveal a profound truth about existence. Reality is not made of static parts, but of relationships in motion. Everything that feels stable, from mountains to stars to human bodies, is built from processes that never rest. The quarks inside your atoms are continually exchanging energy, emitting and absorbing gluons, forming virtual pairs that appear and vanish in trillionths of a second. The matter you think of as permanent is really a ceaseless conversation of forces. Quantum decoherence ensures that this turbulence results in order rather than chaos. It selects from infinite probabilities the few that can coexist coherently, giving rise to the structured universe we inhabit. You, then, are a quantum harmony, a pattern that the universe sustains long enough for awareness to emerge. You are composed of the same ephemeral processes that govern quarks, yet they synchronize in a way that allows thought, memory, and emotion to exist. When you feel something solid, what you are really feeling is the resistance of quantum fields, the refusal of their wave functions to overlap. When you see light reflecting from a surface, you are witnessing photons interacting with the electromagnetic fields of your atoms. Every sensory experience is an interface between decoherence events, between quantum possibilities collapsing into temporary form. So, what does this mean for the concept of self? It means that the identity you experience is not carved in stone. It is a living equation, continuously solved and resolved by the interactions of countless subatomic components. The same process that gives quarks their fleeting properties gives you your sense of continuity. Just as they do not exist in isolation, neither do you. You are an emergent phenomenon, the result of coherence across unimaginable scales. The lesson hidden in this understanding is both humbling and profound. There is no true solidity, only sustained structure. There is no absolute identity, only the persistence of interaction. The universe itself is not built from bricks, but from vibrations, not from things, but from transformations. Every breath you take, every thought that forms, is the cosmos briefly organizing itself into you, a momentary configuration of quantum events, telling its own story before returning to the endless field from which it arose. What holds you together is the same principle that governs quarks: coherence. As long as that coherence persists, so do you. When it dissolves, you do not vanish into nothing. You return to the background field, to the same quantum sea that gave rise to every atom, every star, every heartbeat. You are not made of solid matter. You are a luminous pattern in the vast, shifting dance of the universe, a living echo of the quantum story still being told. A quark doesn't have a fixed position until the universe demands one. So if our bodies are built from atoms, and atoms from protons and neutrons, and those from quarks, what does that make us? Are we tangible beings or structured shadows given temporary form by observation? When a child gazes into a mirror, they see themselves. But what if the reflection is more real than the body itself? What if we are reflections in the quantum field, not metaphors, but literal outcomes of statistical collapse? Everything we feel, pressure, color, heat, emerges from invisible interactions between fields. Solidity isn't because atoms are filled, it's because their fields repel overlap. Beneath that resistance lies nothing, only quarks flickering in and out of existence, holding space together through pure relation. And yet, within this emptiness there is coherence. You feel warmth, you think, you imagine, you believe you are someone, but perhaps identity itself is just another stable pattern, a resonance of atoms, energy, and memory, Protons last for eons because their quark patterns remain balanced. Perhaps humans endure for decades because their neural patterns do. Maybe consciousness is another form of quantum stability, not a soul, but a sustained arrangement of electrical and chemical activity. Just as gluons bind quarks together inside protons, maybe language, emotion, and thought bind us together into something we call self. But like everything else in the universe, we too eventually decay. Our patterns dissolve. Our coherence ends. Yet this isn't tragic. It's natural. Inside every proton, quarks continuously shift and exchange, gluons blink in and out, and virtual particles constantly appear and vanish. What we perceive as stable is, in truth, a dance of change averaged over time. You too are such a dance, changing every heartbeat, every breath, every thought. You lose atoms, rewrite memories, and trade molecules with the world around you. So yes, we are made of shadows, but organized ones. Shadows that reflect light, that resist collapse, that endure long enough to matter. In physics, this process is called emergence, when countless small interactions combine to create something entirely new. A single water molecule doesn't flow, but countless molecules together make rivers and tides. Likewise, a single quark doesn't create meaning, but millions together give rise to thought, love, art, and awareness. Consciousness may simply be the universe's most intricate decoherence, a fleeting moment where countless quantum events synchronize into a being that can ask, "Who am I?" Everything changes. Every structure, every system, every idea is transient. Yet this constant becoming is what gives meaning to existence. You are not a static being. You are a process, a continuation of the Big Bang, smoothed into thought and form. Perhaps that's the true beauty of it all, that in a universe of flickering uncertainty, you are real enough to wonder. So when you look into the mirror, ask yourself, are you seeing a person or a pattern, a shape made of echoes, fields, and fleeting quantum threads? And if that's true, doesn't that make you extraordinary? A shadow that learned how to shine? We have followed quarks across every mystery and through confinement, plasma, fluctuation, and symmetry, and reached the deepest question of all. Are they real? To answer that, we must redefine reality itself. We assume what's real is what we can touch, measure, and see, the chair beneath you, the sky above. But in truth, measurement is only a conversation between observer and observed. Beneath that dialogue lies a quantum world that refuses to settle. Quarks are among the most mysterious entities in the known universe, essential to the structure of matter, yet forever hidden from direct observation. We have never seen a quark, never isolated one, and never held proof of its existence in a conventional sense. Yet everything around us, from the air we breathe to the stars that shine, depends on them. They are the invisible framework holding the physical universe together, and their reality is revealed not through sight, but through the logic and consistency they bring to everything we observe. Without quarks, the laws of physics would unravel, and the stability of matter would become impossible to explain. When scientists first began smashing particles together in high-energy accelerators, they noticed peculiar traces, bursts of energy, decay trails, and scattering patterns that didn't fit the behavior of any known particle. These anomalies pointed towards something smaller, something fundamental. From these patterns, the concept of quarks emerged. We could not detect them directly, but the evidence of their influence was undeniable. Each collision, each flash of radiation, was like a whisper from the unseen. What we call quarks are, in truth, mathematical necessities, entities that make the equations of quantum chromodynamics coherent. They are unseen, yet their fingerprints mark every aspect of the material world. The impossibility of isolating a quark is not due to technological limitation, but to the nature of the universe itself. The strong nuclear force, which binds quarks together inside protons and neutrons, grows stronger the farther apart they are pulled. Unlike gravity or electromagnetism, which weaken with distance, this force intensifies with separation. If you attempt to split a proton by pulling its quarks apart, the energy you add does not set them free. It creates new pairs of quarks instead. The moment of separation becomes the birth of new matter. This phenomenon, called confinement, ensures that no quark will ever exist alone. Reality, at its most fundamental level, is built on relationships rather than individuals. Through these interactions, quarks construct the basic building blocks of the universe. 3 quarks bind to form a proton, another trio forms a neutron, and together they create the atomic nucleus. Around these nuclei dance electrons, shaping the chemistry of life and the structure of the cosmos. Everything tangible, the density of rocks, the warmth of sunlight, the sensation of touch, emerges from the stability quarks provide. Without their precise balance, atoms would fly apart, matter would lose coherence, and the familiar world would dissolve into chaos. Yet quarks challenge our definition of reality. We are accustomed to believing that what is real must be visible or measurable in direct terms. But quarks remind us that the universe does not conform to human expectations. Their existence is inferred through indirect evidence, through consistency, predictability, and the coherence they bring to physical laws. If we were to remove quarks from our understanding of physics, the entire framework of particle theory would collapse. The stability of protons, the existence of atomic nuclei, even the behavior of stars, all would become inexplicable. Thus, we believe in quarks, not because we can see them, but because their presence makes everything else make sense. In this way, they reveal a deeper principle about truth and existence, that visibility is different from reality. Many of the most fundamental aspects of the universe, gravity, time, consciousness, emotion, cannot be seen, yet their influence shapes everything. We cannot point to gravity itself, only to the motion it causes. We cannot isolate time, yet we measure its passing in every heartbeat. We cannot weigh love, fear, or memory, but their presence determines the course of human life. Quarks belong to this same category of unseen essentials, forces and forms that operate below the threshold of perception, giving coherence to the visible world. The evidence for quarks lies not in direct sight, but in patterns. When high-energy particles collide, the results align perfectly with the predictions made by quark theory. The scattering angles, energy distributions, and resonance peaks all tell the same story, that beneath every proton and neutron lies a triad of quarks bound by gluons, the carriers of the strong force. Their existence explains why matter has mass, why atomic nuclei are stable, and why the universe does not dissolve into radiation. These patterns are not coincidences. They are signatures of an underlying order too intricate to dismiss. It is this order, this coherence, that defines what is real. The human mind tends to equate reality with what can be observed through the senses, but science continually expands that boundary. We have never seen an electron either. What we detect are its interactions, the tracks it leaves in a magnetic field, the energy it releases in collision. The same is true for quarks. Their trails are written in the results of experiments, in the decay sequences of particles, and in the energy states that match theoretical predictions with astonishing precision. Each clue strengthens the conviction that, though invisible, quarks are indispensable to the universe's architecture. Philosophically, this invites a profound shift in how we define existence. To exist, something need not be visible. It must only be necessary. Reality, in this sense, is the network of relationships that sustains coherence. Quarks do not simply exist inside matter. They are the reason matter exists at all. Their behavior establishes the stability of atoms, which allows complexity, chemistry, and life to arise. In their absence, no structure could endure, no interaction could persist long enough to form the patterns we recognize as reality. The invisibility of quarks, therefore, is not a weakness of perception, but a statement about the depth of nature. The universe hides its most vital elements beneath layers of emergence. Just as language hides beneath thought and thought beneath neural activity, so too does the visible world rest upon a foundation of unseen forces. The smallest truths are not those we can point to, but those we cannot do without. In this way, the existence of quarks challenges human arrogance. It reminds us that what we perceive is only the surface of a much deeper structure. The physical world is an interpretation, a macroscopic illusion built from quantum relationships we can never witness directly. The solidity of a wall, the light of a star, the pulse in your wrist, all are manifestations of forces that never stand still, particles that cannot be isolated, and interactions that persist only through mutual dependence. To believe in quarks, then, is to accept that necessity defines reality. Their presence is proven not by sight, but by coherence, the way they make the universe intelligible. Remove them, and the logic of physics disintegrates. Keep them, and everything falls into place. That is the measure of truth at the quantum level. Not visibility, but indispensability. Quarks teach us that the essence of existence is not found in what can be seen, but in what holds everything together. They are invisible, yes, but so is gravity, time, or emotion. Each operates silently, yet without them nothing meaningful could exist. The real world, then, is not the one that appears to our eyes, but the one that persists through necessity. A vast, interconnected system of hidden relationships sustaining the illusion of solidity and permanence. Quarks remind us that invisibility does not mean unreality. It means depth, a reality too fundamental for light or sight to reach. They are the unseen grammar of the cosmos, the silent architecture behind matter and motion. To know they exist is to glimpse the universe's underlying logic, a coherence so complete that even without sight we cannot doubt it. Quarks, though forever unseen, are the proof that reality's truest foundations are not what we touch, but what makes everything touchable. Reality, then, is not made of things, but of relationships. You exist not because you are composed of parts, but because your pattern holds together. Like quarks, your being depends on interactions you cannot see. Nothing exists alone. Everything is sustained by balance, resonance, and interconnection. So perhaps quarks are more than particles. They are the universe's poetry, written in the invisible language of spin and charge. Lines that read, "I cannot exist unless you do. I am unseen but essential. I am nothing, yet I make everything possible." And if quarks are real, not because they can be seen, but because everything depends on them, then so are you. You are proof that invisible patterns can take shape, hold meaning, and shine. Because in the end, reality itself is not solid. It is coherence, a whisper of structure in a sea of uncertainty. And that whisper is you. Thank you for joining us on this extraordinary journey through the cosmos here on Frontiers of Infinity. If this exploration has sparked your curiosity, make sure to subscribe and join us next time as we continue unraveling the deepest mysteries of space.